Development Pharmaceuticals in association with Higher Secondary Principals Forum.
So, whatever observations that we saw in this photoelectric effect experiment, let us see whether wave theory can explain this or not. So, the wave theory, so you can see over here, according to wave theory of light, we have already seen wave theory and we know that wave has a continuous energy. According to wave theory, a light greater is the intensity, greater is the energy. So, in wave theory, the intensity of light is proportional to the energy. More is the intensity, more is the energy. So, that means if energy is more, if intensity is more, that means energy of electron, that kinetic energy of electron should be proportional to the intensity of light, which is not happening in the photoelectric effect. Thus, the maximum kinetic energy of the photoelectron should increase with increase in the intensity of light, but the fact is that it increases with the frequency of radiation. Second point, according to wave theory, the energy of radiation is spread all over its wavefront, and calculations show that it takes a very long time for the electron to absorb the sufficient energy and to overcome the work function. That means there is very much time electron takes to absorb the energy if we consider the wavefront, absorption of wavefront. So, that means in this calculation it shows that the photoelectric emission is not instantaneous, but actually the photoelectric emission is instantaneous. So, this also cannot be explained by wave theory of light. So, this will be explained by another theory, and that is nothing but particle theory of light. We cannot explain all these observations with the help of wave theory of light. So, let us understand the explanation of the photoelectric effect given by Einstein with the help of his famous equation, Einstein's photoelectric equation. All these observations in the photoelectric effect experiment were explained by Einstein with the help of his new theory, that is a particle theory of light. So, let us see the Einstein's photoelectric equation, which explains all the observations of photoelectric effect. According to this new theory, what Einstein said is that light is made up of small packets or small quanta or small particles, and each particle is said to be a photon, or it is called a photon. So, light is made up of small packets or small particles called photons, and each this particle, each photon has energy E is equal to h nu. So, if particle has some amount of energy, it will have energy E is equal to h nu, where h is Planck's constant and nu is the frequency of light. When this particle, when this photon get incident on the surface of metal, there are electrons, free electrons. So, when it get incident on the surface, the electron absorbs this energy. So, h nu amount of energy is absorbed by electron. It utilizes this energy and it comes out on the surface. The energy required for electron to come on the surface will be nothing but the work function. So, out of h nu amount of energy, phi 0 amount of energy is utilized by electron to come on the surface, and if this h nu is greater than phi 0, then the electron will come out with certain kinetic energy. So, according to Einstein, this total energy h nu should be equal to the work function phi 0 plus the kinetic energy. So, we get the equation over here, that is H nu should be equal to kinetic energy plus phi 0. So, if I consider this kinetic energy as k, then I will get the equation. This kinetic energy should be maximum kinetic energy of electron. So, I write it as k max, k maximum, and that should be equal to h nu minus phi 0. And this equation is called Einstein's photoelectric equation. Now, let us see further that if the kinetic energy is 0, that means whatever energy is absorbed by the electron, it is just utilized by electron to come on the surface. So, and this will happen for frequency which is a threshold frequency. So, if kinetic energy is k maximum is equal to 0, this will happen for nu is equal to nu 0, that is the threshold frequency. So, if I substitute this, I am going to get 0 is equal to h nu 0 minus phi 0, and this gives the equation for the work function. So, work function phi 0 will be equal to h nu 0. So, that means the threshold frequency for different metal will depend upon the work function of that metal. So, threshold frequency is dependent on the work function. Suppose I substitute this over here, okay, I will get k maximum is equal to h nu minus h nu 0. And further I can write this as k maximum is equal to h nu minus nu 0. This equation completely explains all the observations of this experiment of photoelectric effect. This equation tells us that the maximum kinetic energy of electron is directly proportional to the frequency. So, as frequency is increased, the kinetic energy also will increase. Now, kinetic energy will become equal to 0 if nu is equal to nu 0. So, that means when kinetic energy is 0, that means whatever energy is incident, only the electron will come out on the surface and it will not have any kinetic energy. Also, we can see over here that there is no intensity in the equation. So, that means the kinetic energy does not depend on the intensity. Also, in the explanation, it is said that the moment the photon just get incident on the electrons come out instantaneously. So, this is an instantaneous process. So, this is the explanation of all the observations in photoelectric experiment by the Einstein equation. We will further go to we will modify this equation in such a way that we will get the different other parameters over here with the help of graph. So, further this equation can be written as k maximum, this one, the equation k maximum is equal to h nu minus phi 0. We can write this in terms of potential difference or stopping potential. We know that k maximum is equal to E V 0, that is the potential energy which is applied to the electron. So, V 0 is stopping potential. So, maximum kinetic energy is equal to E V 0. If we substitute it over here, we will get this as E V 0. Okay, we are substituting in this equation. This will be equal to h nu minus phi 0. If I find out V 0, so E will come in the denominator over here and I will get h E nu minus phi 0 by E. This equation is an equation of a straight line where h by E is a slope and minus phi 0 by E is the intercept on y axis. So, if we plot a graph of stopping potential versus frequency of radiation, then stopping potential V 0 nu, and we need intercept over there. So, that means we will get a graph like this. So, this intercept on x axis is our threshold frequency, and intercept on y axis will be minus phi 0 by E, and the slope will be equal to h by E. So, this is the ratio of Planck's constant to the charge of electron. So, from this graph of V 0, that is stopping potential versus frequency, from this we can find out the values of h by E by finding the slope of the graph. Okay, intercept on x axis we get the threshold frequency, intercept on y axis we get the ratio of the work function and work function to electron, phi 0 by E value. So, let us recapitulate all the explanation of Einstein of this particular photoelectric emission. So, first point is that kinetic energy of the photoelectrons depends linearly on the frequency nu and independent of the intensity of incident radiation. If nu 0 is greater than nu, then the kinetic energy is negative, which is not possible. This implies that the photoelectric emission is possible only when h nu is greater than phi 0, that means nu is greater than nu 0. Since nu 0 is phi 0 by h, it follows that greater is the work function phi 0, higher is the threshold frequency. The intensity of radiation is proportional to the number of energy quanta per unit time. Hence, if the intensity is increased, the more number of energy quanta, that means photons, are absorbed by more number of electrons. Thus, the more number of electrons are emitted, causing increase in photocurrent. And last point, in Einstein's picture, the photoelectric effect takes place with when a light quantum is absorbed by an electron. So, that means this is an instantaneous process. So, this explanation gave rise to a new theory, and that is quantum theory of light, or it is nothing but called a particle nature of radiation, and that is nothing but photon. So, let us see this theory. It says that in interaction of radiation with matter, radiation behaves as if it is made up of particle called photons. Each particle, since it is a particle, it will have a momentum. So, it has energy E is equal to h nu and momentum, and this momentum is given by h nu by c, and which is nothing but h by lambda, because c by nu is lambda. So, it is h by lambda, where c is speed of light. The photon energy is independent of the intensity of radiation. The increase in intensity of light of given wavelength lambda means the increase in the number of photon having the same energy E is equal to h nu or h c by lambda. So, if there is increase in intensity, it just increases the number of photons, but it does not increases the energy. It has all the photons with same intensity will have the same energy E is equal to h nu, and all will have the same momentum h by lambda. Photons are electrically neutral and are not deflected by electric and magnetic fields. If there is interaction of photon with particle, photon to photon, or photon with any other particle, there is conservation of energy. So, energy is conserved. There may be absorption of photon, or there will be formation of new photons, but the energy will be conserved in the collision. So, that was regarding the particle nature of light. Now, next, that was the first part. In the second part, let us see the wave nature of matter. The French physicist Louis Victor de Broglie put forward the hypothesis and reasoned that if radiation has a dual nature. So, radiation behaves like a wave, and now we say that radiation also behaves like a particle photon, which has a momentum, which has an energy. So, according to de Broglie, if the momentum formula P is equal to h by lambda is applicable for photon, a particle of light, it should be also applicable for any particle which has momentum. So, there should be, if this formula P is equal to h upon lambda is also applicable for a particle, a matter, that means a wavelength should be associated with this matter and wavelength should be associated with the particle. So, he proposed the wavelength, he gave the formula for wavelength of a particle moving with certain velocity and which has momentum. So, he proposed that the wavelength lambda associated with a particle of momentum p is given by lambda is equal to h by p. H by p, p is momentum m into v. So, it becomes h upon mv. So, if any object is moving with certain velocity v and it has a momentum m, then there will be wavelength associated with it, and that wavelength is given by h upon mv. And this equation is called de Broglie relation, and the wavelength is called the de Broglie wavelength. In the de Broglie relation, its left hand side lambda shows the wave nature, while the right hand side shows the particle nature. So, lambda is on the left hand side, which shows a wave nature. On right hand side there is momentum, mass, okay, it shows a particle nature. The equation 1 also satisfies equation for the momentum of photon, that is P is equal to h nu by c, and therefore, lambda wavelength is c by nu, which is h by p, which is h upon mv. So, if we have any particle moving with velocity v, we can find out how much is the wave or what is the wavelength of that particle by using de Broglie relation lambda is equal to h upon mv, and that is h upon p. So, let us see the wavelength of any object that is moving with certain velocity. According to de Broglie, if particle has got momentum, then there will be wavelength associated with particle. So, let us now calculate the wavelength of some object which is moving with certain velocity. So, let us consider a ball or cricket ball, or let us say this ball has mass of 100 grams, and this is moving with certain velocity v, which is equal to, let us say, 20 meter per second. So, according to de Broglie, the wavelength will be associated with this ball of 100 gram and moving with 20 meter per second, and that lambda, that is wavelength associated with this ball, will be equal to h upon m into v, where h is Planck constant. If we substitute these values, okay, h is 6.63 into 10 raised to minus 34. For the ball, let us say mass is 100 grams, that means it is 0.1 kilogram multiplied by velocity 20. So, this will be equal to 6.63 into 10 raised to minus 34 divided by, this will become 2, and that will be equal to that will be equal to 3.315 into 10 raised to minus 34, and that is will be in meter. So, if we have object, such a object of mass 100 gram and moving with a 20 meter per second, then there will be wave associated with it, and the value of the wavelength will be 3.315 into 10 raised to minus 34 meter. Minus 34 meter is very small value. So, the wavelength is absolutely negligible. So, that is why we cannot notice a wave like behavior of a particle which are macroscopic or a bigger particle. So, we can find out, or we can calculate the wavelength of the particles which are very small, which have a very small mass, a momentum, and moving with certain velocity. Let us find the wavelength of electron which is moving in the potential difference of V volt. So, the formula for wavelength lambda will be equal to h by p. So, we have to find out the momentum of electron. So, this can be found with the help of the equation. We know that kinetic energy K will be equal to EV, that is V is the potential through which the electron is moving. Now, we can write the kinetic energy K is equal to half mv square. We can write this as half m square v square divided by m, which is equal to half, this will become p square by m. So, p square will be equal to 2 mk, and therefore, p will become equal to square root of 2 mk. But the kinetic energy K is equal to EV. So, we can write this P is equal to square root of 2 m E V. And now, if we apply our formula for wavelength, then this lambda will be equal to h by p, and that will be equal to h by square root of 2 m E V. If we substitute all the values over here of h, m, e, we will get this lambda is equal to 1.227 divided by square root of v in nanometer. So, this relation gives us, if we know the potential difference through which electron is moving, we can find out lambda value, wavelength value by substituting V over here, and lambda value can be found there. So, we can see in the slide that we already worked out this formula, lambda of electron is equal to 1.227 upon root of V, that is potential difference in nanometer. If you substitute some voltage over there 120 volt, we can get directly whatever is the wavelength for that particular voltage, and here it is coming to 0.112 nanometer. And this wavelength is of the order of spacing between the atomic planes in the crystal. Next we will see what is de Broglie hypothesis and Heisenberg's uncertainty principle. This I will just take in brief. According to Heisenberg's principle, uncertainty principle, the position and momentum of a particle cannot be measured simultaneously with unlimited precision. So, there will be always uncertainty in the position and momentum, and according to Heisenberg principle, if delta x is the uncertainty in position and delta p is uncertainty in momentum, then this product comes to be greater than or equal to h by 4 pi. So, there are two options. If momentum is constant, that delta p will be equal to 0 and delta x will be equal to infinity. That means wave is spread all over the space, and if both delta x and delta p are finite, then the wavelength will be over the wavelength, a central wavelength. The wavelength will be over the central wavelength, and it will spread along the central wavelength. So, delta x will have some value, delta p also will have some value, and this actually was explained according to de Broglie hypothesis. The spread of wavelength will result into spread in the momentum of the electron, which incorporates the Heisenberg's principle. So, here what happens is, when delta x has some value, delta p has some value, the matter wave associated with electron is a wave packet extending over some finite region. with different wavelengths spread around the central wavelength. This is shown by the figure. These are the two possible waves. In first wave, delta x is infinity, that is wave is spread all over the space, and in second diagram you can see that delta x and delta p has a finite value, and there wave is spread around a central wavelength. Coming to the last part of this topic, and that is nothing but a verification of the de Broglie hypothesis that is done by Davison and Germer. This is called a Davison and Germer experiment, a verification of wavelength of an electron. So, let us see now the wavelength found by de Broglie with the help of equation lambda is equal to h upon mv is same equal to the one which is found by this experiment or not. So, this experiment consists of a vacuum chamber. You can see that there is vacuum chamber, and there is electron gun which is the source of electron. It is a beam of electron. This beam is collimated, it is made narrow, and this is focused on a nickel target. So, when it is focused on the nickel target, there is scattering of this electron. So, when there is scattering of electron, it scatters with different angles. These scattered electrons are collected by the moving collector over here, and this collector is connected to a galvanometer. So, it can record the number of electrons at that particular spot. So, this gives actually a constructive interference of all those electrons which are scattered by the different layers of nickel or different layers of atoms over there in the nickel target. This actually gives a just like a diffraction pattern, and from that diffraction pattern, the maximas and minimas, with the help of that we can find out the wavelength of the electrons which are coming out over there. And by using that diffraction pattern, wavelength found for the voltage is equal to 54 volt, and that angle of scattering for theta is equal to 50 degree, the wavelength found was 0.165 nanometer. And if you use de Broglie relation, and if you substitute that 54 volt as a voltage in de Broglie relation, the value that you get is 0.1669. So, which is very close to the value the experimental method. Thus, there is an excellent agreement between the theoretical value and the experimentally obtained value of de Broglie wavelength, and that proves the de Broglie hypothesis that particle also behave like a wave. This also proved by recently in 1989, one Japanese scientist Tonomura, he demonstrated a single electron build-up of interference pattern. It is actually interference, double slit interference experiment done with the electrons, and you can see in the figures there is a pattern with less electrons. You cannot see it properly, but in the last figure you can see the bright and dark fringes like thing over there, and from those we can find out the wavelength of these electrons, and it shows that particle also has the wave nature, and that proves the de Broglie hypothesis. Just to summarize and some applications, wave nature of light explains reflection, refraction, diffraction, interference, and all these we studied in wave optics and ray optics. Particle nature of light explains photoelectric effect and Compton effect that involves energy and momentum. A photocell is a technological application of photoelectric effect, where electric energy can be produced with the help of photon, that is light. The familiar phenomenon of seeing an object is described by both wave and particle nature. If you consider the phenomenon of seeing the object, the gathering of light can be explained, gathering of light by the lens, eye lens can be explained by wave nature of light, but the absorption of light by rods and cone cells of retina can be explained with the help of particle nature of light. The matter wave or de Broglie waves support the Bohr's atomic theory, that is quantization of angular momentum, that we are going to study in topic number 12, and it is the second postulate of Bohr's theory. The de Broglie hypothesis has been basic for development of modern quantum mechanics. The wave properties of electrons have been utilized in the design of electron microscope, which has resolution higher than optical microscope. So, this is the direct application of de Broglie hypothesis. Before we come to end of this session, okay, I would like to share with you two things. One is whatever Einstein said about the dual nature of light, and then second thing, I will share one cartoon which will tell you about the dual nature of light, and we have already understood the dual nature of light. You will enjoy that cartoon. So, let us first start with whatever Einstein said about dual nature of light, and I quote, "It seems as though we must use sometimes the one theory and sometimes the other, while at times we may use either. We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomena of light, but together they do." That means, together light as a particle and a wave, together it explains completely phenomena of light. And this is the cartoon, particle and wave duality. That is all in this lecture for today. Thank you and have a nice day.
Prudent Scholars, powered by Lupin Pharmaceuticals.
अब आपकी सुरक्षा आपके हाथों में। ल्यूपी सेफ हैंड सैनिटाइजर, आपका और चेन्नई सुपर किंग्स का फर्स्ट लाइन ऑफ डिफेंस। अब आपकी सुरक्षा आपके हाथों में। ल्यूपी सेफ हैंड सैनिटाइजर, आपका और चेन्नई सुपर किंग्स का फर्स्ट लाइन ऑफ डिफेंस। अब आपकी सुरक्षा आपके हाथों में। ल्यूपी सेफ हैंड सैनिटाइजर, आपका और चेन्नई सुपर किंग्स का फर्स्ट लाइन ऑफ डिफेंस।